And let's just go back and once again refresh our memories. So about elastic potential energy, and what the formula is 1/2 kx squared. And let's remind ourselves what those actual variables stand for. The k right there is our spring constant. And what that tells you is it tells you how squishy or stretchy is your spring. If you have a high K value, then that means it's less stretchy. It means it's stiffer. And the units, just so we remember how the units go, the units for K are newtons per meter. That's how that works. Up here, this X value is the distance that the spring was squished or stretched. Distance squished or stretched. All right. Now let's just go ahead and actually set up a problem here, and we'll use elastic potential energy. And let's see, I'm going to take a spring. I'll just draw the spring over here. And let's say that it has a spring constant of 20 newtons per meter. All right, and what I'm going to do is I'm going to put a mass on top of it and launch it. This is going to be just like the marble launchers that we did in class. So there's our mass. We're going to launch this mass. It's going to come up and it's going to come down. What I want to know is how high does the mass go? That was our marble in class. And I'm measuring it from the top of its, where the spring was squished. Right? I'm kind of ignoring this distance down there. What I need to know is I need to know how much was the spring initially squished. Let's put our X value and let's make that 10 centimeters. And the other thing I need to know is what's the value of the mass inside of here. And so we'll draw that there. Let's say that our mass is 100 grams. That's significantly heavier than your marble, right? So now I want to set this up. How do I figure out how high does the mass go? And the way we're going to do this is once again with conservation of energy. So I'm going to say that the sum of the initial energy is equal to the sum of the final energy. Good? Well, let's think about what kinds of energy we actually have here. What we're talking about is we have spring energy, that's elastic potential energy in the beginning, and then we have potential energy, gravitational potential energy at the end. And that's really it. So we don't have to worry about anything else. So what we're going to have is a 1/2 kx squared over here, and we're going to have an mgh over there. And now we're just solving for what h equals. Easy, let's do the algebra. H equals 1/2, keep our kx squared divided by mg. Now we can actually just plug in the numbers and it should work out pretty well. Let's pay attention to our units though. We want to make sure everything works out in the right kind of units. H equals 1/2. Our K is 20 newtons per meter. Our X was 10 centimeters, so that's 0.1 meters. Got to square that. And we divide that by our mass, which was 100 grams. That's 0.1 kilograms times our g, 10 meters per second squared. Right? Now we just have to start multiplying all these things out and figuring out how this is going to work. So let's see here. We're going to get, keep switching back and forth with the colors. H equals, let's see, that 2 is going to cancel with that 20. So we're going to get 10 times 0.1 squared is 0.01 divided by 0.1 times 10 is 1. And we get H equals 0.1 meter. That's going to be the height that the mass is going to go. Right? one thing we can pay attention to is, once again, just back up here, this is our conservation of energy problem. So always set the initial energy equal to the final energy, and in this case, we just had spring energy on this side turns into potential energy on this side. A different way we could set this problem up, and I'll just set up the problem and I won't really intend to solve it, just keep the video shorter, is I could turn it into kinetic energy instead of potential energy. So let's say instead that I set the spring this way and I put the mass at the end of the spring. As long as I have no friction, I can figure out how fast is the mass going after I let it go from the spring. Same thing here, conservation of energy. I add up all my initial energy, and that's going to equal to adding up all the final energy. Great. This time we're just going to say spring energy, 1/2 kx squared, equals kinetic energy, 1/2 mv squared. Then I can solve for v, and I can get the answer that way. So all these energy problems, really, the point is figuring out what kind of energy do I have at the beginning, what kind of energy do I have at the end, just setting them equal to each other.